So this is the 15th session in the subject of digital communications, and we are going to study the calculation for bit error probability in the binary detection. So let us start. So let us first of all revise our concepts of binary detection, which we have already studied. Last time we studied the block diagram and also studied how the binary detection is done. So let's quickly revise that. Input passes through filters. We have seen that you require a matched filter and followed by an equalizer filter. Matched filter is for maximizing the SN ratio, and equalizer filter is used for reducing the inter-symbol interference. And at the output of these filters, the output is sampled at the end of the bit time t, based on which you take your decision. So if the input is S1t plus nt, the sampled output is Z equal to A1 plus N0. Notice that if there was no noise, this component will be 0 and Z will be simply be equal to A1 if S1t was transmitted. But since noise is present and it's a random noise, this Z is a random variable, continuous random variable, and it will have a definite conditional density function. We shall see that. We studied that last time. We'll again look at it. Alright, so if there is no noise, then the output which is sampled at the bit time t will be equal to A1, but it actually becomes a random variable because of the noise. Okay. But if the input is S2t plus nt, then the output is Z equal to A2 plus N0. So again, this is a random variable, but its average value will be A2. Whereas the average value of the sampled signal will be equal to A1 if S1t is sent. Okay. Now we have studied last time that we have got a threshold A1 plus A2 by 2, which is designated by say lambda 0, and this is compared with Z. So remember last time we have seen that if Z is greater than lambda 0, then you conclude that S1t was sent. We are of course assuming in this case that A1 is greater than A2. And if the value of Z is less than the threshold, then we conclude that S2t was sent. Okay. So if we look at this pictorially, this is the A1 value which is greater than A2. Z may lie anywhere, but as long as it is greater than lambda by lambda 0, that is greater than the threshold, we conclude that S1t was sent. Now suppose S1t was sent, but because of the noise, Z is not above lambda 0, but it's below lambda 0. Z is somewhere here. Then you will conclude that S2t was sent, whereas actually S1t was sent. So the error will occur whenever if S1t is sent and Z is less than lambda 0. Error will also occur if S2t is sent and Z is not between these two values but is between these two values, then again the error will occur. So based on this, we are going to study the calculation of bit error probability. But before doing that, let us study the concept of noise margin. So this is whatever I have been saying here. Z is the sampled value and this is compared with lambda 0. Okay. Next, let us discuss the concept of noise margin. Suppose S1t is sent and there is no noise, then what you get at the output, sampled output is A1. But suppose there is a noise and the value of the noise is negative, so that the actual detected value goes below A1. But as long as this value lies between lambda 0 and A1, you don't commit an error because you conclude that S1t was sent, which is actually sent. But as soon as the negative value of the noise, if it exceeds A1 minus lambda 0, so it comes somewhere here, then the error will occur. That is why this value A1 minus lambda 0, which is also equal to lambda 0 minus A2 because of the symmetry, is called as the noise margin. So what is the noise margin? Let's calculate that. Noise margin is A1 minus lambda 0. That is equal to A1 minus A1 plus A2 by 2. Remember, this is our threshold. So when you solve this, you will get A1 minus A2 by 2. So this is the noise margin. And actually you will get the same value whether you take A1 minus lambda 0 or you take lambda 0 minus a2, you will get the same expression, because this occurs at the center of these two, between these two values. So this tells us that larger the difference between a1 and a2, larger is this value, more difficult it will be for the noise to cause an error. So understand this, that qualitatively we expect the bit error probability to be small, larger is the difference between A1 and A2. And of course, if the noise is smaller, after all, if there is no noise, there is no error at all. But if the noise is smaller, so that it doesn't go beyond this when S1T is sent, then error will not occur. So qualitatively we should understand that the larger the difference and smaller is the noise, bit error probability will be smaller. But if this difference is smaller, then of course the error is more likely and the bit error probability will be higher. And also if the noise is larger, then again the bit error probability will be larger. So we want to do this calculation quantitatively now. So for that we look at the conditional density functions again, plot them, and look at the whole thing graphically in terms of conditional density functions. So this is our Pz stroke S1. So if S1T is transmitted, then the likelihood of S1 is maximum at Z equal to A1. And if S2T is transmitted, then likelihood of S2 is maximum if Z is equal to A2. Okay. Now suppose S1T is transmitted. So if Z is above lambda 0, then we have seen no error occurs. But if Z is less than this, anywhere from minus infinity right up to lambda 0, then the error will occur. So this shaded area here, this actually extends asymptotic to minus infinity. This shaded area will, if you calculate this area, it will give you bit error probability. Remember, this is the conditional density function. So if you calculate the area under that, it will give you the probability that the variable lies in that particular range. So if S1T is transmitted and Z lies anywhere from minus infinity up to lambda 0, then the error will occur. Similarly, if S2T is transmitted, then the error will not occur if Z is less than lambda 0. But if it is greater than lambda 0 right up to infinity, then again the error will occur. So these conclusions can be written down mathematically like this. If S1 is transmitted, the error will occur if Z2 is between minus infinity to lambda 0, as we discussed. So the probability that error occurs given that S1 is transmitted is from minus infinity to lambda 0, you integrate the conditional density function. Similarly, the error will occur if S2 is transmitted when you integrate from gamma naught to infinity, then again you will get the error. So the bit error probability can be calculated as the sum of these two joint probabilities, and by Bayes' theorem, because these are mutually exclusive events, so you can simply add up these two in order to calculate the net bit error probability. So this is the joint probability which says that error occurs given that error occurs and either S1 or S2 is transmitted. So by Bayes' theorem we can rewrite it in this form. Okay, so let us expand this. When we expand it, we get P E stroke S1 P S1 plus P E stroke S2 into PS2. Now assuming PS1 equal to PS2 is equal to 1 by 2, assuming this uniform probability distribution of the source, if you assume that, and also because of the symmetry, PE stroke S1 is equal to PE stroke S2. In that case, if you substitute these two conditions in this, it's easy to see that the bit error probability can be calculated either by calculating the probability, conditional probability that error occurs given that S1 is transmitted, or probability of error occurring given that S2 is transmitted. So let us do this calculation. So we'll assume that, let's say, S2 was transmitted So PB is equal to A1 plus A2 by 2 from gamma lambda 0 to infinity. And now we substitute for this. So this is A1 plus A2 by 2 to infinity. This is 1 upon sigma n under root 2 pi exponential. This is the standard equation for Pz stroke S2, which we studied last time. Now, in order to use understand the tables are available for the standard normal Gaussian function. So we need to change the variable in order to convert this into standard Gaussian function. So what we do is we make a change of variable and define a new variable u equal to z minus a2 divided by sigma n. So clearly this will become u squared, okay? And when you substitute this, you can calculate what is the lower limit. That will change now and it will be in terms of u. So this calculation is easy. Of course, when z is infinity, u is also infinity. So the upper limit will not change, the lower limit will change, and that will be equal to a1 minus a2 upon 2 sigma n. All you have to do is to substitute for z from here and you will be able to get this. And then since u is given by this, dz can be replaced, so this sigma n cancels and you will get 1 upon under root 2 exponent e raised to minus u squared by 2 du. So this is now in the standard normal Gaussian form, and as we have studied, if you calculate this over this, calculate the area over these limits, then you get the q function, q of a1 minus a2 upon 2 sigma n. Refer to the last lecture and it's easy to see that this is so. So bit error probability will be given by the q function, which is a1 q of a1 minus a2 upon 2 sigma n. So what we discussed a short while ago, that larger the difference between a1 and a2 and smaller the noise, this quantity within the parameters, within the parenthesis, will be higher, and higher this value, remember, qx is lower, so bit error probability will be lower when this difference is larger and the noise is smaller, as we expect. So that's all in this particular session. In this session, we have essentially seen how to calculate the bit error probability, and we have obtained a mathematical expression for this, and it depends on the q function.